we are deep diving into black holes for 1 hour long. If you are getting ready to sleep or want something to listen to in the background, this video is for you. Let's dive in. Imagine standing at the edge of reality itself, where the laws of physics as we understand them begin to break down and whisper secrets that challenge everything we think we know about the universe. Black holes represent one of the most profound mysteries in all of cosmology. And today, we are going to explore them in a way that reveals not just what they are, but the beautiful and strange implications they hold for the very fabric of space-time itself. Let us begin with something that few people ever discuss when talking about black holes, something called the firewall paradox. This paradox emerged in 2012 when physicists Joseph Polchinski, Ahmed Almheri, Donald Marolf, and James Sully realized that there might be a fundamental contradiction in our understanding of what happens at the event horizon of a black hole. According to quantum mechanics, information cannot be destroyed. But according to Stephen Hawking's calculations, black holes should evaporate over time through a process called Hawking radiation. And when they do, all the information about what fell into them would be lost forever. The firewall paradox suggests that to preserve information, there might need to be a wall of incredibly high-energy radiation right at the event horizon that would incinerate anything trying to cross it. This contradicts Albert Einstein's equivalence principle, which says that someone falling into a black hole should not notice anything special when crossing the event horizon. It should be a smooth transition. The paradox remains unsolved, and it represents one of the deepest conflicts between quantum mechanics and general relativity that we have ever encountered. Connected to this is the black hole information paradox itself, which has haunted theoretical physics for decades. When Stephen Hawking first calculated that black holes emit radiation and eventually evaporate, he concluded that the radiation would be completely thermal, meaning it would carry no information about what fell into the black hole. This would mean that if you threw an encyclopedia into a black hole and waited for it to evaporate, all the information in that encyclopedia would be permanently lost from the universe. This violates a fundamental principle of quantum mechanics called unitarity, which states that information about a quantum state must always be preserved in some form. Physicists have proposed various solutions to this paradox. Some suggest that information is somehow encoded in the Hawking radiation in subtle correlations that we have not yet understood. Others propose that information might be stored at the event horizon itself in a two-dimensional holographic form. Still, others think that the paradox reveals a deep flaw in our understanding of space-time at the quantum level. Leonard Susskind and Gerard 't Hooft developed the holographic principle partly in response to this paradox, suggesting that all the information contained in a volume of space can be encoded on the boundary of that space, like a hologram. This principle has become foundational in modern theoretical physics, influencing string theory and our understanding of quantum gravity. Now let us turn our attention to rotating black holes, which are far more complex than the simple non-rotating black holes that are usually discussed. In 1963, Roy Kerr discovered an exact solution to Einstein's field equations that describes a rotating black hole. These Kerr black holes have not one but two event horizons, an outer one and an inner one. Between these two horizons lies a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation. This effect is called frame dragging, and it means that nothing in the ergosphere can remain stationary, not even light. Everything must rotate in the same direction as the black hole, though objects in the ergosphere can still escape if they have enough energy. The inner horizon of a Kerr black hole is called the Cauchy horizon, and it represents a boundary beyond which we cannot predict the future evolution of spacetime, using the laws of physics as we know them. Crossing the Cauchy horizon would lead to a region where causality breaks down, and time travel might become possible, at least in principle. However, most physicists believe that the Cauchy horizon is unstable and would be destroyed by quantum effects before anything could actually cross it. The ergosphere of a rotating black hole enables a remarkable process called the Penrose process, named after physicist Roger Penrose, who discovered it in 1969. In this process, you can actually extract energy from a rotating black hole. Here is how it works. You send an object into the ergosphere and arrange for it to split into two pieces. One piece falls into the black hole, while the other piece escapes. If you do this correctly, the piece that escapes can have more energy than the original object, with the extra energy coming from the black hole's rotation. The black hole slows down slightly and loses some of its mass in the process. This means that rotating black holes are stores of rotational energy that could, in principle, be harvested by a sufficiently advanced civilization. Some scientists have even speculated that certain energetic phenomena we observe in the universe might be natural Penrose processes occurring around rotating black holes. Beyond the Penrose process, there is an even more efficient energy extraction mechanism called the Blandford-Znajek process, which applies to rotating black holes surrounded by magnetic fields and accretion disks. In this process, magnetic field lines threading through the ergosphere can extract rotational energy from the black hole and channel it outward in powerful jets. This mechanism is thought to power some of the most energetic phenomena in the universe, including quasars and the jets from active galactic nuclei that can extend for millions of light years. The efficiency of this process can be remarkable, converting up to 42% of the black hole's mass energy into outgoing radiation and kinetic energy in the jets. For comparison, nuclear fusion, which powers stars, converts less than 1% of mass into energy. This makes rotating black holes surrounded by magnetic fields potentially the most efficient energy generators in the cosmos. Hawking radiation itself deserves much deeper exploration than it usually receives. When Stephen Hawking calculated in 1974 that black holes should emit thermal radiation, it shocked the physics community because it meant that black holes are not entirely black after all. The mechanism behind Hawking radiation involves quantum fluctuations in the vacuum of space. According to quantum field theory, empty space is not truly empty, but is filled with virtual particle and antiparticle pairs that constantly pop into existence and annihilate each other. Near the event horizon of a black hole, one member of such a pair can fall into the black hole while the other escapes. To an outside observer, it appears as though the black hole is emitting radiation. The temperature of this radiation is inversely proportional to the black hole's mass, which means that smaller black holes are hotter than larger ones. A black hole with the mass of our Sun would have a temperature of only about 60 nanokelvins, far colder than the cosmic microwave background, so it would actually absorb more energy than it emits. But a black hole with the mass of a mountain would be much hotter, and a black hole with the mass of an aircraft carrier would have a temperature of billions of degrees. These small black holes would evaporate rapidly, ending their lives in a burst of energy. The time it takes for a black hole to evaporate completely goes as the cube of its mass, so stellar mass black holes would take far longer than the current age of the universe to evaporate, while microscopic black holes would vanish almost instantly. The fact that black holes have a temperature means they also have entropy, which is a measure of disorder or the amount of information needed to describe a system. Jacob Bekenstein first proposed in 1972 that black holes must have entropy proportional to the area of their event horizon. Hawking's calculation confirmed this and provided the exact relationship. Black hole entropy is proportional to the area of the event horizon divided by 4 times the Planck length squared. This is remarkable because for ordinary objects, entropy is proportional to volume, not area. The fact that black hole entropy is proportional to area is one of the main pieces of evidence supporting the holographic principle. It suggests that the information content of a black hole is encoded on its 2-dimensional surface, rather than in its 3-dimensional volume. This has profound implications for our understanding of spacetime and quantum gravity. It suggests that what we perceive as 3-dimensional space might actually be a holographic projection from information encoded on a 2-dimensional surface at the boundary of the universe. Primordial black holes represent another fascinating and often overlooked aspect of black hole physics. Unlike stellar black holes that form from the collapse of massive stars, primordial black holes could have formed in the very early universe, less than a second after the Big Bang, from density fluctuations in the hot, dense plasma that filled space at that time. These primordial black holes could have a wide range of masses, from as small as the Planck mass, which is about 22 micrograms, up to thousands or even millions of solar masses. Small primordial black holes, with masses less than about 1 billion kilograms, would have evaporated by now through Hawking radiation, but larger ones could still exist. Some scientists have proposed that primordial black holes might make up some or all of the dark matter that we know exists in the universe, but have not yet directly detected. Dark matter makes up about 85% of the matter in the universe, and we know it exists because of its gravitational effects on galaxies and galaxy clusters. But we do not know what it is made of. Primordial black holes would interact only through gravity, just like dark matter, making them potential candidates. However, various observations have placed strong constraints on the abundance of primordial black holes in different mass ranges, and it now seems unlikely that they make up all of the dark matter, though they might still contribute to some fraction of it. Extremal black holes represent a special and theoretically important class of black holes that exist at the boundary of what is physically possible. An extremal black hole is one where the charge or angular momentum is at the maximum possible value for a given mass. For a charged black hole, this means the electric charge is equal to the mass in appropriate units. For a rotating black hole, it means the angular momentum is equal to the mass squared. At this extreme limit, the 2 event horizons of a charged or rotating black hole merge into one, and the black hole has 0 surface gravity and therefore 0 Hawking temperature. This means an extremal black hole would not evaporate through Hawking radiation. Extremal black holes have bizarre properties. They have an infinite throat region, meaning that if you could somehow survive crossing the event horizon, you would fall for an infinite amount of time as measured by your own clock before reaching the singularity. The near-horizon geometry of an extremal black hole has a special symmetry that makes it particularly amenable to mathematical analysis, and extremal black holes have played an important role in developments in string theory and the study of black hole microstates. The concept of black hole microstates is itself a deep and fascinating topic that connects black holes to string theory and quantum mechanics. In classical general relativity, all black holes with the same mass, charge, and angular momentum are identical. They are characterized completely by just these 3 numbers, a principle known as the no-hair theorem. This seems to conflict with the fact that black holes have entropy, because entropy counts the number of different microscopic configurations that could give rise to the same macroscopic state. If all black holes with the same mass, charge, and angular momentum are identical, how can they have entropy? String theory provides a potential answer. In string theory, what we perceive as a black hole is actually a bound state of many different fundamental objects, like strings and branes, and there are many different ways these objects can be arranged to produce a black hole with the same macroscopic properties. These different arrangements are the microstates, and counting them in certain special cases produces exactly the entropy predicted by Bekenstein and Hawking. This is one of string theory's most concrete successes, though it has only been achieved for special types of black holes, and extending it to more realistic black holes remains an active area of research. The singularity at the center of a black hole represents a place where our current theories of physics break down completely. General relativity predicts that all the matter that falls into a black hole gets compressed into an infinitely dense point with infinite curvature of spacetime. This is clearly unphysical, and most physicists believe that quantum effects, which are not included in general relativity, must become important before the true singularity is reached. We need a theory of quantum gravity to understand what really happens at the center of a black hole. Various proposals exist. Loop quantum gravity suggests that quantum effects might cause the collapse to bounce, creating a new expanding region of spacetime on the other side, possibly connecting to a white hole or even spawning a new universe. String theory suggests that the singularity might be resolved by stringy effects that become important at the Planck scale, preventing the formation of a true geometric singularity. Some speculate that the singularity might be replaced by a fuzzy quantum region described by a complicated quantum superposition of different geometries. We simply do not know, and this ignorance points to one of the deepest unsolved problems in theoretical physics. White holes are the time reverse of black holes, and they represent another exotic prediction of general relativity that probably does not exist in nature. While a black hole is a region of space-time that you can enter but never escape, a white hole is a region that you can leave but never enter. White holes would expel matter and energy rather than absorbing it. The problem is that white holes appear to be extremely unstable and would violate the second law of thermodynamics. Any small perturbation would likely cause a white hole to collapse into a black hole. Furthermore, the time reversal symmetry that leads to white holes assumes that the universe itself is time symmetric, which it is not due to the arrow of time defined by increasing entropy. Nevertheless, white holes are interesting as mathematical solutions and have been studied in the context of cosmological models and theories about the Big Bang. Some speculative ideas suggest that the Big Bang itself might have some characteristics of a white hole, or that black holes and white holes might be connected through wormholes, creating shortcuts through spacetime. Wormholes are tunnels through spacetime that could, in principle, connect distant regions of the universe, or even different universes entirely. The simplest type of wormhole solution to Einstein's equations is called the Einstein-Rosen bridge, and it connects the interiors of two black holes. However, this type of wormhole is not traversable. If you tried to go through it, you would encounter the singularity before reaching the other side, and the wormhole throat would pinch off before anything could pass through. Traversable wormholes require exotic matter with negative energy density to hold them open against collapse. While quantum field theory allows for negative energy densities in certain circumstances, the amounts and distributions required for a traversable wormhole seem to be far beyond anything we could create or find naturally. Some physicists have explored whether advanced civilizations might be able to create and maintain traversable wormholes, perhaps using quantum vacuum manipulation or Casimir effects, but these ideas remain highly speculative. Wormholes also lead to potential causality violations and time travel paradoxes if they connect regions of spacetime that are separated in time as well as space, adding further complications to their physical plausibility. The detection of gravitational waves has opened up an entirely new way to study black holes and has confirmed many predictions of general relativity. On September 14, 2015, the Laser Interferometer, gravitational wave observatory, known as LIGO, detected gravitational waves for the first time from the merger of two black holes about 1.3 billion light-years away. This detection was a triumph of experimental physics and observational astronomy, confirming a century-old prediction by Einstein. The two black holes, with masses of about 29 and 36 times the mass of the Sun, spiraled into each other and merged to form a single black hole of about 62 solar masses. The missing 3 solar masses were converted into gravitational wave energy that rippled across space-time at the speed of light. Since that first detection, dozens more black hole mergers have been observed, along with neutron star mergers and even collisions between black holes and neutron stars. These observations have revealed a previously hidden population of stellar mass black holes and have provided precise tests of general relativity in the strong field regime where gravitational effects are extreme. The observations have also raised puzzles, such as the existence of black holes, more massive than theoretical models predicted could form from stellar collapse, suggesting new formation channels or different stellar evolution paths than we previously understood. The concept of photon spheres adds another layer to understanding black hole geometry. A photon sphere is a spherical region around a black hole where gravity is strong enough that photons, which are particles of light, can orbit the black hole in circular paths. For a non-rotating black hole, the photon sphere is located at 1.5 times the Schwarzschild radius, which is the radius of the event horizon. At the photon sphere, light can orbit the black hole, creating the possibility for weird effects like seeing the back of your own head if you were somehow hovering there. The photon sphere is unstable, meaning that any small perturbation will cause a photon either to fall into the black hole or escape to infinity. For rotating black holes, the situation is more complex, with different photon sphere radii, depending on whether the photon is orbiting in the same direction as the black hole's rotation or opposite to it. The photon sphere plays an important role in determining what an observer would see when looking at a black hole. It affects the appearance of the black hole's shadow, which is the dark region visible in images like the famous first image of a black hole in the galaxy, Messier 87, taken by the Event Horizon Telescope in 2019. That brings us to the remarkable achievement of imaging black holes directly. The Event Horizon Telescope is not a single telescope, but a global network of radio telescopes that work together as an Earth-sized virtual telescope through a technique called very long baseline interferometry. By combining data from telescopes in locations including Arizona, Hawaii, Mexico, Chile, Spain, and the South Pole, astronomers were able to resolve the shadow of the supermassive black hole at the center of Messier 87, a giant elliptical galaxy about 53 million light-years away. The black hole has a mass of about 6.5 billion times the mass of the Sun, and its shadow has an angular size of about 40 microarcseconds, roughly equivalent to seeing a bagel on the Moon from Earth. The image shows a bright ring of emission surrounding a dark central shadow. The emission comes from hot gas orbiting the black hole in an accretion disk, heated to billions of degrees by friction and magnetic fields. The shadow is about 2.6 times larger than the event horizon due to gravitational lensing effects that bend light rays around the black hole. The image confirmed predictions of general relativity about the size and shape of black hole shadows and ruled out some alternative theories of gravity. In 2022, the Event Horizon Telescope released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, showing similar features and further confirming our understanding. Accretion disks around black holes are sites of some of the most energetic processes in the universe. When matter falls toward a black hole, it does not usually fall straight in, but rather forms a rotating disk of material, gradually spiraling inward. Friction within the disk converts gravitational potential energy into heat, causing the disk to glow across the electromagnetic spectrum, from radio waves to X-rays. The inner parts of the accretion disk closest to the black hole are the hottest and brightest, reaching temperatures of millions or even billions of degrees. At these temperatures, the disk emits X-rays and gamma rays. The processes in accretion disks are incredibly complex, involving magnetohydrodynamics, which is the study of electrically conducting fluids in magnetic fields, turbulence, and relativistic effects from the black hole's intense gravity. Magnetic fields in the disk can become twisted and amplified, leading to the formation of jets, which are narrow beams of particles and radiation that shoot out perpendicular to the disk at speeds approaching the speed of light. These jets can extend for millions of light years and are visible across cosmological distances, making supermassive black holes with active accretion disks, called active galactic nuclei, some of the brightest objects in the universe. Quasars are among the most luminous objects known, powered by supermassive black holes actively accreting matter at prodigious rates. The term quasar is short for quasi-stellar radio source because when they were first discovered in the 1960s, they appeared as point-like sources of radio emission that looked like stars but had unusual spectra. Later observations revealed that quasars are the extremely bright centers of distant galaxies, powered by black holes with masses of millions to billions of solar masses, swallowing gas at rates of tens or hundreds of solar masses per year. A single quasar can outshine its entire host galaxy, which might contain hundreds of billions of stars. The most distant quasars we have observed are so far away that we see them as they were when the universe was less than 1 billion years old, less than 7% of its current age. The existence of such massive black holes so early in cosmic history poses a challenge for theories of black hole formation and growth. It is not entirely clear how black holes could grow so large so quickly, and various mechanisms have been proposed, including rapid accretion onto seed black holes, direct collapse of massive gas clouds without forming stars first, or mergers of many smaller black holes. Tidal disruption events represent a dramatic phenomenon where a star wanders too close to a supermassive black hole and is torn apart by tidal forces. As the star approaches the black hole, the gravitational force on the near side of the star becomes significantly stronger than on the far side, stretching the star into a long strand of stellar material. About half of this material becomes bound to the black hole and falls back in an accretion flow, while the other half is ejected at high speeds. The fallback material creates a bright flare lasting months to years, as it is heated to extreme temperatures while spiraling into the black hole. These events can be detected across vast distances and provide a way to discover otherwise quiescent black holes that are not actively accreting material. They also offer a unique probe of relativity and black hole physics. Observations of tidal disruption events have revealed complex emission patterns including X-ray, ultraviolet, and optical light, as well as sometimes radio emission from relativistic jets. Each event is somewhat different, depending on the mass and type of star, the mass and spin of the black hole, and the geometry of the encounter, making them a rich area for study. The formation of stellar mass black holes through the death of massive stars involves some of the most violent events in the cosmos. When a star with an initial mass greater than about 20 times the mass of the Sun exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core of the star collapses in less than a second, reaching densities higher than that of an atomic nucleus. For the most massive stars, the collapse does not stop at the neutron star stage, but continues past the point of no return, forming an event horizon and creating a black hole. The outer layers of the star bounce off the collapsing core and are blown into space in a core collapse supernova, one of the brightest explosions in the universe. However, for the most massive stars, much of the outer material might also fall into the black hole, resulting in a weaker supernova, or even a failed supernova, where the star collapses and disappears with relatively little visible fireworks. Exactly which stars produce which outcomes depends on details of stellar structure, rotation, mass loss throughout the star's life, and possibly metallicity, which is the abundance of elements heavier than hydrogen and helium. These details are still being worked out through combinations of theoretical modeling and observations of supernova and their remnants. Intermediate mass black holes represent a mysterious and sparsely populated region of the black hole mass spectrum. These black holes would have masses between about 100 and 100,000 solar masses, filling the gap between stellar mass black holes formed from individual stars and supermassive black holes found in galaxy centers. Intermediate mass black holes are important because they might be the seeds that grow into supermassive black holes, but we have only tentative evidence for their existence. Some of the best candidates come from ultraluminous X-ray sources, which are X-ray emitting objects in nearby galaxies that are too bright to be explained by typical stellar mass black holes, accreting at normal rates. Some of these might be intermediate mass black holes accreting matter, though alternative explanations involving stellar mass black holes accreting at super Eddington rates are also possible. Another potential location for intermediate mass black holes is in the centers of globular clusters, which are dense spherical collections of old stars. Dynamical simulations suggest that repeated mergers of stars and stellar remnants in dense cluster cores could build up intermediate mass black holes, and there is some observational evidence suggesting their presence in a few globular clusters, though the evidence remains controversial. Supermassive black holes sit at the centers of nearly every large galaxy, including our own Milky Way. These behemoths can have masses ranging from millions to tens of billions of solar masses. The supermassive black hole at the center of our galaxy, Sagittarius A star, has a mass of about 4 million solar masses. The most massive known black holes, found at the centers of giant elliptical galaxies, can reach masses exceeding 10 billion solar masses. These enormous black holes likely grew through a combination of gas accretion and mergers with other black holes over billions of years. There appears to be a tight relationship between the mass of a galaxy's central supermassive black hole and the properties of the galaxy's bulge, particularly the velocity dispersion of stars in the bulge. This suggests that the growth of supermassive black holes and the evolution of their host galaxies are intimately connected through feedback processes. When a supermassive black hole actively accretes material and shines as an active galactic nucleus, the energy output can heat or expel gas from the galaxy, affecting star formation and the overall evolution of the galaxy. Gravitational lensing by black holes creates spectacular optical effects that allow us to probe both the nature of black holes and the distribution of matter in the universe. When light from a distant source passes near a massive object like a black hole, the space-time curvature caused by the black hole's gravity bends the light's path, acting like a lens. For a perfectly aligned point source behind a black hole, this creates an Einstein ring, a circular image surrounding the black hole. More generally, Gravitational lensing by black holes can magnify distant objects, create multiple images, or distort their shapes. Microlensing events, where a black hole passes in front of a more distant star, cause the star to brighten temporarily as the black hole's gravity focuses the star's light toward us. These events have been used to search for black holes in our galaxy, including potential primordial black holes that might make up dark matter. Strong gravitational lensing by supermassive black holes in distant galaxies can magnify and distort background galaxies, sometimes creating spectacular arcs or multiple images visible in deep space telescope observations. The innermost stable circular orbit around a black hole represents the closest distance at which matter can orbit stably before being inexorably drawn inward. For a non-rotating black hole, the innermost stable circular orbit is at 3 times the Schwarzschild radius, or 6 times the gravitational radius. Inside this radius, there are no stable circular orbits, and anything on a circular orbit would spiral into the black hole. For rotating black holes, the situation depends on whether the orbit is in the same direction as the black hole's rotation or opposite to it. For orbits in the same direction as the rotation, the innermost stable circular orbit can be as close as the event horizon itself for maximally rotating black holes. This means that matter can orbit much closer to a rotating black hole than to a non-rotating one, and this has observable consequences. The inner edge of an accretion disk sits at the innermost stable circular orbit, and the closer matter can get to the black hole, the more energy can be extracted from its gravitational field, leading to more luminous emission. Observations of X-ray emission from accretion disks, particularly features like the broad iron fluorescence line, can be used to measure the spin of black holes by determining where the inner edge of the accretion disk is located. Quasi-periodic oscillations in the X-ray emission from black holes provide another way to probe the strong gravity region close to the event horizon. These are nearly periodic variations in brightness, with timescales ranging from milliseconds to hundreds of seconds, depending on the black hole's mass. The physical origin of quasi-periodic oscillations is still debated, but they are thought to arise from processes in the inner accretion disk or from oscillations of the disk itself. One class of models attributes high-frequency quasi-periodic oscillations to orbital motion at or near the innermost stable circular orbit, with different oscillation frequencies corresponding to different modes of motion, such as orbital frequency, radial epicyclic frequency, and vertical epicyclic frequency. If this interpretation is correct, observations of quasi-periodic oscillations provide a direct probe of spacetime geometry in the strong field region, and can be used to test general relativity and measure black hole parameters. Lower frequency quasi-periodic oscillations might be related to precession of the accretion flow, or to instabilities in the disk. The no-hair theorem states that isolated black holes in general relativity are characterized completely by only 3 externally observable parameters: mass, electric charge, and angular momentum. All other information about the matter that formed the black hole or fell into it is lost to external observers. This is sometimes summarized by saying, black holes have no hair, meaning no additional distinguishing features. The theorem applies to black holes that have settled down into a stationary state and are not accreting matter or otherwise changing. In practice, astrophysical black holes are unlikely to have significant electric charge, because any charge would quickly be neutralized by attracting oppositely charged particles from the surrounding plasma. So real black holes are effectively characterized by just 2 parameters: mass and angular momentum. The no-hair theorem has been tested observationally through gravitational wave observations of merging black holes, which have confirmed that the final merged black hole rings down to a stable state characterized by mass and spin, with the ring-down frequencies matching the predictions of general relativity. However, the no-hair theorem might not hold in modified theories of gravity or in quantum gravity, and testing it in different regimes remains an active area of research. The ring-down phase of a black hole merger provides particularly clean tests of general relativity in the strong field regime. After two black holes merge, the resulting single black hole is initially distorted and asymmetric. It then settles down to a symmetric stationary state by emitting gravitational waves in a characteristic pattern of damped oscillations, like a struck bell ringing. The frequencies and damping times of these ring-down modes depend only on the mass and spin of the final black hole and are precisely predicted by general relativity. By measuring the ring-down signal in gravitational wave detections, physicists can test whether the observed frequencies and damping times match the predictions. So far, all observations have been consistent with general relativity, but more precise measurements could potentially reveal deviations that would point to new physics. The ring-down is also interesting because it probes the newly formed black hole very close to the event horizon, where quantum gravity effects might be important. Echoes after black hole mergers represent a speculative but intriguing possibility that has been the subject of recent research. Some theories of quantum gravity predict that the event horizon of a black hole might not be a perfectly smooth, one-way membrane, but could have structure at the Planck scale that would cause gravitational waves to partially reflect off of it. If this were true, then after the main ring-down signal from a black hole merger, there might be faint echoes of the gravitational wave signal bouncing back and forth inside the newly formed black hole, leaking out in a series of pulses separated by the light travel time around the black hole. Several groups have claimed tentative evidence for such echoes in LIGO and Virgo data, but the signals are at the edge of detectability and remain controversial. Other groups have analyzed the same data and found no convincing evidence for echoes. Future gravitational wave detectors with better sensitivity might be able to definitively detect or rule out echoes, providing a direct probe of quantum gravity effects at the event horizon. The cosmic censorship conjecture is one of the most important unsolved problems in general relativity, and it concerns the nature of singularities. Roger Penrose proposed in 1969 that singularities formed by gravitational collapse must always be hidden inside event horizons, never naked and visible to the outside universe. A naked singularity would be a place of infinite curvature and density that could be seen from afar, and its existence would represent a catastrophic breakdown of predictability in physics, because we could not predict what might emerge from it. The weak cosmic censorship conjecture states that singularities arising from physically reasonable initial conditions are always hidden inside black holes. The strong cosmic censorship conjecture states that spacetime cannot be extended beyond a Cauchy horizon in a physically reasonable way. Both conjectures remain unproven, though there are many suggestive results supporting them. Some exotic solutions to Einstein's equations, such as the inner horizon of a charged or rotating black hole, appear to violate strong cosmic censorship, but these solutions may be unstable in ways that restore censorship. Understanding whether cosmic censorship holds is crucial for the predictability of general relativity and has implications for quantum gravity. The membrane paradigm offers an alternative way to think about black holes that can be very useful for understanding their behavior in astrophysical contexts. Instead of thinking about the event horizon as a geometric boundary in spacetime, the membrane paradigm treats it as if it were a physical membrane with properties like viscosity, electrical conductivity, and temperature. This is not meant to suggest that the horizon literally is a physical surface, but rather that for many purposes, especially when analyzing accretion and electromagnetic processes around black holes. It is mathematically equivalent and often more intuitive to think of it this way. The membrane appears to have properties that would be expected from its entropy and temperature. For instance, it has an effective viscosity that causes rotating matter near the horizon to transfer angular momentum to the black hole, spinning it up. The membrane has electrical resistivity that affects how currents flow in the magnetosphere around the black hole. Using the membrane paradigm, physicists can apply techniques from fluid dynamics and electromagnetism to study black hole systems without having to work directly with the complications of curved spacetime near the event horizon. Charged black holes, described by the Reissner-Nordström solution, if non-rotating, or the Kerr-Newman solution if rotating, have very different properties from uncharged black holes. A charged black hole has an outer and inner horizon, similar to a rotating black hole, but the separation between them depends on the charge rather than the spin. As the charge increases toward the extremal limit, the two horizons approach each other and eventually merge. Beyond the extremal limit, the solution describes a naked singularity with no horizon at all, though cosmic censorship suggests that such objects cannot form in nature. In practice, astrophysical black holes are unlikely to have significant net electric charge because space is filled with plasma that would quickly neutralize any charge imbalance. However, charged black holes are important theoretically, particularly in studies of black hole thermodynamics and in string theory, where various types of charges associated with different gauge fields play important roles. The Schwarzschild radius defines the event horizon of a non-rotating, uncharged black hole and represents the distance from the center at which the escape velocity equals the speed of light. It is proportional to the mass of the black hole, specifically 2 times the gravitational constant times the mass divided by the speed of light squared. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For a black hole with the mass of Earth, it would be about 9 millimeters. This means that to turn Earth into a black hole, you would have to compress all of its mass into a sphere smaller than a marble. The average density inside the Schwarzschild radius depends on the mass. For stellar mass black holes, the average density is extraordinarily high, many times nuclear density. But for supermassive black holes with billions of solar masses, the average density inside the event horizon can actually be quite low, comparable to or even less than the density of air. This is because the Schwarzschild radius increases linearly with mass, while volume increases with the cube of the radius, so density decreases as mass increases. The gravitational redshift near black holes produces observable effects that have been measured in several systems. As light climbs out of a gravitational well, it loses energy and its wavelength increases, shifting toward the red end of the spectrum. Near a black hole, this effect becomes extreme. Light emitted from close to the event horizon can be redshifted by large factors, and light from the event horizon itself would be redshifted to infinite wavelength, essentially becoming undetectable. This gravitational redshift has been measured in the spectra of material orbiting close to supermassive black holes. Iron fluorescence lines from the inner accretion disk show characteristic asymmetric, broadened profiles due to a combination of Doppler shifts from the orbital motion and gravitational redshift from the black hole. By fitting models to these line profiles, astronomers can measure the spin of the black hole and test general relativity in the strong field regime. The gravitational redshift has also been measured from stars orbiting close to Sagittarius, a star at the center of our galaxy, providing independent confirmation of the black hole's mass. Magnetospheres around black holes are structured regions of magnetic field that can extend far beyond the event horizon and play crucial roles in accretion and jet formation. While black holes themselves have no magnetic field, the ionized gas in the accretion disk and surrounding space carries magnetic fields that thread through the black hole's ergosphere and horizon. These fields can become highly organized, with field lines connecting the disk to the jets or wrapping around the black hole. The interaction between the rotating black hole and the magnetic field extracts energy through the Blandford-Znajek process mentioned earlier. Magneto-hydrodynamic simulations of accretion flows onto black holes have revealed complex dynamics, including the development of turbulence driven by the magneto-rotational instability, which is a fundamental mechanism for transporting angular momentum outward in the disk and allowing matter to fall inward toward the black hole. Understanding these magnetospheres is crucial for explaining the observed properties of accreting black holes across the mass spectrum. X-ray binaries are stellar systems where a black hole or neutron star orbits a normal star and accretes material from it, producing intense X-ray emission. In these systems, the black hole or neutron star pulls gas from its companion star, either through a stellar wind or by overflowing the Roche lobe, which is the region around each star where its gravity dominates. The transferred material forms an accretion disk around the compact object, heating up and emitting X-rays. X-ray binaries have been crucial for discovering and studying stellar mass black holes. The first strong black hole candidate was Cygnus X1, discovered in the early 1970s. By measuring the orbital motion of the visible star and applying Kepler's laws, astronomers could determine the mass of the unseen compact companion. If the mass exceeds about 3 solar masses, the maximum possible mass for a neutron star, then the compact object must be a black hole. Dozens of stellar mass black holes have now been identified in X-ray binaries in our galaxy, with masses ranging from about 5 to 20 solar masses. Microquasars are X-ray binaries that show some of the same features as quasars, including relativistic jets, but on much smaller scales, appropriate for stellar mass black holes. The jets from microquasars can be observed moving at substantial fractions of the speed of light, and they provide laboratories for studying jet physics much closer to home than distant quasars. Some microquasars show dramatic outbursts where the system transitions between different accretion states. In the low hard state, the accretion rate is relatively low. The X-ray spectrum is hard, meaning dominated by high-energy photons, and steady jets are present. In the high soft state, the accretion rate is higher. The spectrum is softer with more lower-energy photons, and the jets are usually suppressed or absent. The transitions between these states are associated with changes in the geometry and physics of the accretion flow, and are not yet fully understood. Studying microquasars helps us understand the physics of accretion and jet formation that applies to supermassive black holes in distant galaxies. Soft X-ray transients are a class of X-ray binaries that spend most of their time in quiescence, showing only weak or no X-ray emission, but occasionally undergo outbursts lasting months, where the X-ray luminosity increases by factors of millions or billions. These outbursts are thought to be caused by thermal ionization instabilities in the accretion disk. When the disk is cool and neutral, matter builds up slowly from mass transfer from the companion star. Eventually, the disk becomes dense enough that a portion ionizes, increasing its opacity and causing it to heat up. This triggers a thermal runaway that propagates through the disk, causing it to brighten dramatically and dump material onto the black hole. After the outburst, the disk cools and returns to the low state until enough material accumulates to trigger the next outburst. These systems have provided valuable insights into accretion disk physics and allow us to study black holes in both active and quiescent states. The prospects for detecting Hawking radiation from astrophysical black holes are unfortunately negligible because the temperature of stellar mass or larger black holes is so incredibly low. For a black hole with one solar mass, the Hawking temperature is about 60 billionths of a Kelvin, and it decreases inversely with mass. The cosmic microwave background has a temperature of about 2.7 Kelvin, so any astrophysical black hole is much colder than its surroundings and will absorb more radiation than it emits. Only black holes with masses much smaller than 1 billion kilograms would be hot enough to be detectable sources of Hawking radiation, and such small black holes would evaporate rapidly. If primordial black holes with masses around 1 billion kilograms formed in the early universe, they would be evaporating right now and might be detectable through gamma-ray bursts or other signatures. Several searches for such signals have been conducted but have not found convincing evidence. Nevertheless, Hawking radiation remains one of the most important theoretical predictions connecting quantum mechanics, general relativity, and thermodynamics, even if we cannot observe it directly from real black holes. Analog black holes provide another approach to studying Hawking radiation in laboratory settings. These are not actual gravitational black holes, but rather systems where some other kind of wave, such as sound or light, behaves mathematically like a particle in the curved spacetime of a black hole. For example, in a flowing fluid, sound waves can be carried along by the flow. If the fluid flows faster than the speed of sound in some region, sound waves cannot escape from that region, creating an acoustic horizon analogous to an event horizon. According to theory, such acoustic black holes should emit an analog of Hawking radiation in the form of thermal phonons. Similar analog systems can be created using superfluids, Bose-Einstein condensates, optical media, and other systems. Several experiments have reported observations of analog Hawking radiation in these systems, though the interpretation remains somewhat controversial. While these analog systems do not involve gravity and cannot address questions about quantum gravity, they do demonstrate that the basic mechanism underlying Hawking radiation is robust and appears in many different physical contexts. The final parsec problem refers to a challenge in understanding how supermassive black hole binaries merge in galactic nuclei. When two galaxies merge, their central supermassive black holes sink toward the center of the merged galaxy through dynamical friction with stars and dark matter. However, calculations suggest that this process becomes inefficient when the black holes are separated by about 1 parsec, which is roughly 3 light-years. At this point, they have ejected or scattered most of the stars on orbits that would intersect their path, and further orbital decay through dynamical friction becomes very slow. Yet we observe that supermassive black holes do merge, as evidenced by gravitational wave detections and the existence of single massive black holes in galaxy centers. The resolution to this problem likely involves additional mechanisms that can drive the black holes together in the final stages. These might include interactions with gas in a circumbinary disk, which can exert torques on the binary, or 3-body interactions with stars in a rotating or triaxial nuclear star cluster that can replenish the loss cone of stars interacting with the binary. Understanding the final parsec problem is important for predicting the rates and properties of supermassive black hole mergers that will be detected by future gravitational wave observatories. The Laser Interferometer Space Antenna, known as LISA, is a planned space-based gravitational wave observatory that will open up a completely new window on the universe. Unlike ground-based detectors like LIGO and Virgo, which are sensitive to high-frequency gravitational waves from stellar mass compact object mergers, LISA will observe low-frequency gravitational waves from supermassive black hole mergers, extreme mass ratio in spirals, where stellar mass compact objects spiral into supermassive black holes and other sources. LIGO will consist of 3 spacecraft arranged in an equilateral triangle, with sides about 2.5 million kilometers long, following Earth's orbit around the Sun. Laser beams will travel between the spacecraft, and tiny changes in the distances caused by passing gravitational waves will be measured with exquisite precision. LIGO is expected to detect supermassive black hole mergers throughout the universe, providing insights into galaxy formation and evolution, black hole growth, and the structure of space-time on cosmological scales. It should also detect thousands of stellar mass compact objects spiraling into supermassive black holes in galactic nuclei, providing detailed maps of the space-time around these black holes and stringent tests of general relativity. Extreme mass ratio inspirals are systems where a stellar mass compact object, such as a black hole or neutron star, spirals into a supermassive black hole in a galactic nucleus. These systems are important targets for LISA because they produce gravitational wave signals that last for years and contain enormous amounts of information about the space-time geometry around the supermassive black hole. As the small object orbits, it traces out the structure of space-time in incredible detail, and the gravitational wave signal encodes this information. Analyzing these signals will allow physicists to map the space-time around supermassive black holes and test general relativity with unprecedented precision. Any deviations from the predictions of general relativity, such as those that might arise from additional fields or modifications to gravity, could be detected. The challenge is that analyzing extreme mass ratio in spiral signals requires solving the equations of motion to extremely high accuracy, taking into account not just the background space-time, but also the small object's own gravitational field and the back reaction of the emitted gravitational waves on the orbit. This is an active area of research in gravitational wave theory. Pulsar timing arrays represent yet another approach to detecting gravitational waves, sensitive to even lower frequencies than LIGO. Pulsars are rapidly rotating neutron stars that emit beams of radio waves, and some of them, called millisecond pulsars, are incredibly stable clocks. By monitoring the arrival times of pulses from an array of millisecond pulsars distributed across the sky over many years, astronomers can search for correlated timing variations that would be caused by gravitational waves passing between Earth and the pulsars. The main expected source of gravitational waves at these frequencies is a stochastic background from the population of supermassive black hole binaries throughout the universe. As these binaries orbit each other, they emit gravitational waves that create a background hum pervading space. Several pulsar timing arrays around the world have been collecting data for over a decade, and recent results have provided strong evidence for this gravitational wave background. Though confirming it definitively and characterizing its properties requires more data. Pulsar timing arrays may also be sensitive to individual, particularly massive or nearby supermassive black hole binaries, though detections of individual sources are more challenging. Black hole bombs are a theoretical phenomenon related to superradiance around rotating black holes. Superradiance occurs when a wave with a frequency below a certain threshold is scattered by a rotating black hole and emerges with greater amplitude than it had initially, extracting rotational energy from the black hole in the process. This is closely related to the Penrose process, but applied to waves rather than particles. If the wave is somehow confined near the black hole, perhaps by a massive field that cannot propagate to infinity, then it can be repeatedly amplified through superradiance, growing exponentially and extracting large amounts of energy from the black hole's rotation. This is called a black hole bomb. The most studied example involves ultralight bosonic particles, such as axions, which are hypothetical particles predicted by certain extensions of the standard model of particle physics. If such particles exist with the right mass, they could form clouds around rotating black holes through superradiance, creating a black hole bomb that would spin down the black hole and emit gravitational waves or other radiation. Searches for such signals in gravitational wave data and electromagnetic observations have placed constraints on the properties of ultralight bosons, showing how black holes can be used as laboratories for particle physics. The future of black hole research is bright, with numerous observational and theoretical advances on the horizon. Gravitational wave astronomy will continue to mature, with upgrades to existing detectors improving their sensitivity and enabling detections of more distant and diverse sources. New detectors like LISA, the Einstein telescope, and Cosmic Explorer will open up new frequency bands and dramatically increase detection rates. Electromagnetic observations will also advance, with next-generation telescopes providing more detailed views of black hole environments across the spectrum. The Event Horizon Telescope continues to improve, with plans to add more stations and higher frequency observations that will provide sharper images and movies of black hole dynamics. Advances in numerical simulations, running on ever more powerful computers, will provide better theoretical predictions to compare with observations. And theoretical work will continue to push toward a complete theory of quantum gravity that can resolve the puzzles and paradoxes that black holes present. Black holes also raise profound philosophical questions about the nature of reality, information, and our ability to understand the universe. The information paradox asks whether the universe is fundamentally deterministic, as quantum mechanics suggests, or whether information can truly be lost, violating the basic principles of quantum theory. The cosmic censorship conjecture asks whether nature hides her singularities, or whether there are circumstances where predictability breaks down completely. The holographic principle suggests that our three-dimensional world might be a projection from a two-dimensional boundary, challenging our basic intuitions about space and reality. These questions go beyond technical physics to touch on fundamental issues about what we can know and how the universe operates at the deepest level. As we contemplate these mysteries, it is worth reflecting on how far we have come in our understanding of black holes. Just over a century ago, Einstein published his theory of general relativity, and within months, Carl Schwarzschild found the first black hole solution. For decades, black holes were regarded as purely mathematical curiosities, extreme solutions to Einstein's equations that probably had no counterpart in the real universe. It was not until the 1960s that physicists began to take black holes seriously as astrophysical objects, spurred by the discovery of quasars and the development of new mathematical techniques for studying general relativity. The first black hole candidate, Cygnus X1, was identified in the early 1970s. The first image of a black hole came in 2019. Gravitational waves from merging black holes were first detected in 2015. Each of these discoveries confirmed predictions and opened up new questions. We now know that black holes are not rare exotic objects, but are common throughout the universe, playing crucial roles in galaxy evolution and the structure of the cosmos. Thank you for joining me on this deep exploration of black holes. These cosmic enigmas continue to challenge our understanding and inspire new questions about the nature of reality, space-time, and the fundamental laws of physics that govern our universe. As we peer into the darkness of these mysterious objects, we find not emptiness, but a richness of phenomena that pushes the boundaries of human knowledge and imagination. May your dreams tonight be filled with the wonders of curved space-time, quantum mysteries, and the infinite possibilities that black holes represent in our quest to understand the cosmos.